Europa hides a secret beneath its frozen crust. There's an immense global ocean, potentially teeming with life, sealed and hidden away in darkness for millennia. Recently, NASA launched its Europa Clipper mission, which is yet to unravel the mysteries of this alien world. Beneath the frozen surface, hydrothermal vents may create ideal conditions for life forms to thrive, just as they do in the deepest parts of Earth's oceans. But how do we explore these extraterrestrial worlds, and what secrets might they reveal? Clipper is one of NASA's most ambitious endeavors, aimed at studying the habitability of icy moons. It was launched in October 2024. It was built to study Europa, one of Jupiter's moons long suspected to harbor a huge subsurface ocean beneath its thick, icy shell. The Clipper mission is set to reach Europa in the 2030s, and its primary goal is to assess whether this moon can support life as we know it. Equipped with top-of-the-line tools, the spacecraft will embark on a multi-year journey through the solar system. Once it reaches Jupiter's orbit, Europa Clipper will make dozens of close flybys of Europa, gathering unprecedented data about its structure, composition, and most importantly, the possibility of life on this moon. The mission's particularly significant because for the first time, a spacecraft will focus on the viability of an oceanic world, expanding our understanding of where life might potentially exist in the universe. Though Europa's surface may seem frozen and uninhabitable, it could be one of the most promising life-sustaining environments beyond Earth. Beneath its icy exterior lies a global ocean, potentially holding more than twice the volume of Earth's oceans. It's theorized that the thick ice layer shields the ocean from harsh radiation, while tidal forces from Europa's proximity to Jupiter cause significant flexing and heating, possibly keeping the water in a liquid state. On board Europa Clipper is an impressive suite of scientific instruments, each designed for specific tasks. The ice-penetrating radar will help scientists measure the thickness of the ice and determine if there's any interaction between the ocean and the surface. The spacecraft's spectrometers will be used to analyze the chemical composition of the surface, examining it for compounds that might hint at biological processes. Meanwhile, magnetometers will map Europa's magnetic field, providing clues about the ocean's depth and salinity. Thanks to these repeated flybys, Europa Clipper will be able to provide researchers with detailed insights into the icy shell, the ocean, and the potential hydrothermal activity of this moon. The data gathered by the mission will be crucial in determining whether Europa's ocean contains the chemical energy necessary to sustain life. However, Jupiter's radiation poses a significant challenge for any spacecraft in its vicinity. The planet's magnetic field is 20,000 times stronger than Earth's. It traps charged particles that race around the system at incredible speeds, creating an intense radiation zone bombarding nearby moons with ionizing radiation, including Europa. For Europa Clipper, the challenge lies not only in surviving this high-energy environment, but also in protecting the delicate onboard electronics from being damaged by the radiation. The electronic systems of the craft, including the central computing units, scientific tools, and communication systems, are shielded from radiation. The protective casing, made from a combination of aluminum and zinc, is a vital defense against radiation exposure. But even with this protection, Jupiter's radiation is so intense that some components, particularly the transistors used in Europa Clipper's instruments, may still prove to be vulnerable. Transistors known as MOSFETs, metal oxide semiconductor field effect transistors, are essential for controlling the flow of electricity throughout the spacecraft. These components are especially sensitive to ionizing radiation, which can alter their electrical properties and lead to failure. Recent tests have shown that these transistors fail at lower radiation doses than initially predicted, and that raises concerns about their reliability once Europa Clipper reaches Jupiter's orbit. To mitigate the risk, NASA engineers to assess how many transistors could go out of commission during the mission and how severe the consequences might be. They're exploring ways to extend the life of these components through software and operational workarounds, such as limiting exposure to the highest radiation zones and using redundancy in systems where possible. Despite the precautions, there's no simple solution. The spacecraft's electronics vault was sealed in 2023, making any hardware changes impossible without significant delay. Over the last few months, the mission team has been weighing the risk of semiconductor vulnerability against the high cost and potential delay associated with unsealing the vault and replacing parts. If the electronics stop working prematurely, it could jeopardize the operation of critical systems. However, the mission's design includes built-in redundancies and operational flexibility, allowing the team to work around certain failures by relying on backup systems. NASA's task is to ensure these failures do not impede the mission's primary scientific objectives, especially the exploration of Europa's icy surface and the ocean beneath it. Now, let's take a closer look at these oceans. So as we've already mentioned, there are vast oceans hidden beneath the icy shells of Europa and Enceladus, potentially some of the most promising places for finding life beyond Earth. It's believed that these concealed oceans, kept in a liquid state by the tidal forces of their parent planets, contain key ingredients necessary for life: liquid water, energy sources, and essential chemical elements such as oxygen. But how exactly could we measure the potential for life in these alien oceans? The answer lies in how oxygen and other chemical elements are produced and distributed beneath the icy layers. On Europa, one of the most important factors for assessing habitability is oxygen. Although Europa is constantly bombarded by high-energy particles from Jupiter's magnetic field, this radiation is more than just a threat to technology. It could also contribute to oxygen production. When these charged particles collide with Europa's icy surface, they break water molecules into hydrogen and oxygen. While most of the hydrogen escapes into space, some of the oxygen remains in the Moon's atmosphere or enters the subsurface ocean through the cracks and brine channels in the ice. The current theory is that this water-splitting process is one of the main ways oxygen enters Europa's ocean. However, recent studies have shown that previous estimates of oxygen production on Europa may have been overstated. New data, particularly the measurements taken by NASA's Juno probe, indicate that the amount of molecular oxygen present around Europa is much lower than previously believed. This data suggests a more limited oxygen entry into the subsurface ocean, potentially narrowing the range of conditions in which life could exist. According to the latest data, Europa produces around 26 pounds of molecular oxygen per second. That's a far cry from the earlier estimate of up to 2,000 pounds per second. This revised figure has led scientists to reconsider the question of how much oxygen actually reaches the ocean and whether this amount is sufficient to support oxygen-dependent life forms. Despite the lower than expected oxygen production numbers, Europa remains a prime candidate for harboring life. Even at these low levels, this Jupiter moon produces enough oxygen to sustain life in a unique, potentially energy-efficient form. The process is occurring on Europa, where oxygen may seep into the ocean through cracks in the ice, may resemble Earth's deep-sea environments, where life exists without sunlight, relying on chemical energy. In particular, this energy could be provided by hydrothermal vents on the ocean floor. Hidden beneath thick ice in eternal darkness, these vents may offer chemical and thermal energy supplied by hydrothermal activity, just as hydrothermal vents discovered in Earth's deep oceans. These vents, acting as natural chimneys, release mineral-rich heated water from the rocky depths of the Moon, creating a potential haven for the emergence and flourishing of life. On Earth, hydrothermal vents are home to unique ecosystems that don't rely on sunlight. Instead of depending on photosynthesis, the life forms around them derive energy from a chemical reaction between water and minerals, a process known as chemosynthesis. Astrobiologists believe that if life exists on this moon, it could thrive in a similar way. Unlike Earth's deep-sea black smokers, which are powered by the planet's molten core and can reach temperatures over 700 degrees Fahrenheit, hydrothermal vents on these icy moons are expected to be much cooler. The absence of a molten core on Europa and Enceladus raise questions about the sustainable existence of high-temperature vent systems. However, new models suggest that low-temperature hydrothermal vents may have persisted on these moons for billions of years, providing long-term stability and a source of heat. These low-temperature vents should operate similarly to those found on Earth's seabed, for example, along the Juan de Fuca Ridge in the Pacific Ocean. On Earth, cold seawater is drawn into the seabed, where it circulates through ancient volcanic rocks, gradually heating up before re-emerging through other vent openings. This process not only heats the water, but also alters the chemical composition, producing the necessary ingredients for chemosynthetic life. Organisms like tube worms and extremophiles thrive by utilizing hydrogen sulfide and methane released from the seabed. Europa is intriguing not only because of its hidden ocean, but also due to its dynamic surface activity. Recent observations, particularly from NASA's Juno mission, have provided new insights into the water plumes, jets of vapor escaping from beneath the moon's icy crust. These plumes, first spotted by the Hubble Space Telescope and now confirmed by multiple missions, give scientists a tantalizing glimpse of what lies beneath Europa's frozen shell. When the Juno spacecraft went past Europa in 2022, it captured high-resolution images of the Earth's surface, revealing complex features such as ridges, chaotic terrain, and scars that may indicate regions of recent activity. Also, the most significant findings were areas believed to be the source of water vapor plumes. These towering jets shooting as high as 120 miles into space are thought to arise from cracks in the icy crust where salty liquid from the subsurface ocean meets the near vacuum of space and quickly evaporates.